Today's topic is torque. Torque is a force that's applied tangent to the circle at some distance from the center. Torque causes rotation around a point. In this example, the point of rotation is right here. It takes force to start an object rotating. And in this example, the force that starts that rotation is right here in this spot. And it causes a rotation along this circular path. And as it does so, the object rotates with this radius, which is also called a moment arm. The force you apply should be perpendicular to the displacement. If not, you're going to have to use sine or cosine. Let's say you have this bolt and this wrench. If you want to wrench something, you don't want to push the wrench this way. You're not going to get any results. And you don't want to pull the wrench this way. You're not going to get any results. The best way to use the wrench is to apply a force perpendicularly or tangent to the circle. In this example up here, you can see that the person is applying a force downwards and at an angle, and that component of the force isn't going to cause it to rotate. Only this component will, which is why you would have to use sine and cosine if the force is not perpendicular to your displacement. This force is going to be more effective the farther it is from the axis of rotation and if it's perpendicular to the axis of rotation. Once again, let's say you have a bolt. There is a reason why if you want to tighten a bolt, it's really difficult to do with your fingers, because as you rotate a bolt with your fingers, the radius or distance from the axis of rotation is only this much. Whereas if you have a bolt and you want to use a wrench, a short wrench is going to be less effective than a longer wrench. So the longer moment arm or radius you have, the more effective your force will be. Torque is represented by this symbol right here. This is the Greek letter tau. And I assume that tau is used for torque because t is taken as time and capital T is taken as period. So they're running out of symbols, so they decided to pick the Greek equivalent of t, which is the letter tau. And you can see that torque equals force times radius. So you apply, for example, a force at a larger radius and it'll create more torque, just like we discussed. And its units are newtons and meters, and that makes sense because it's force times radius. You can also see it includes the sine theta, and that is because if you apply a force at an angle other than 90 degrees, you're only going to include the part of the force that is tangent to the circle or perpendicular to the radius. In this example over here, the force and the radius are 90 degrees from each other. So in the equation, you would say sine of 90, which is 1. So if it's at a 90-degree angle, it typically doesn't include the angle in the problem because you can assume that it's just going to be the sine of 90 or 1. And you can effectively ignore this part of the equation since it's just multiplying by 1. If the force is acting at an angle, though, you'll have to include that sine theta. Concerning torque, we say that a counterclockwise rotation is considered positive. The torque would be out of the page and bolts are loosened, whereas a clockwise rotation is considered to be negative. The torque would be into the page and bolts would be tightened down. You might remember as righty-tighty being negative and lefty-loosey being positive. An object that is leaning might take more force to upright because of the larger distance of its moment arm. In this example, we have 4 forces with the same strength, and we're looking downwards on a door. You can see this is the top view of the door, and this is the hinge. Which force would be most effective in opening the door? And you'd correct if you said force 1, because force 1 is being applied perpendicularly to the door, and it has a large radius. Force 4 would also open the door, but since it has a smaller radius, it would not be quite as effective. Force 2 would have no effect because it's at 0 degrees. So this would cancel out and create 0 torque. And lastly, this force right here is acting at an angle, which means that we would only be able to consider the portion of this force that is perpendicular like this. Here's our next example. We have a 150 kilogram man who's at the end of a massless diving board. Here's our diving board. This is the diving board's point of rotation, which is sometimes called a fulcrum. His mass is applying a force at the end of the diving board, which is a distance of 2 meters away. How much torque does he apply at the base where the board is attached? So you know that torque is force times radius times sine theta. And the force that he's applying right here is his force of gravity. We can fill that in as 150 kilograms times 9.8, which together makes a force, and multiply that by the radius, 2 meters. And with that, we get 2,940 Newton meters of torque. What if there are two torques? For example, what if there's an object that's balancing, like on a seesaw? These two objects are in what's called rotational equilibrium. When we're talking about linear systems, we say that an object is at rest if all the forces cancel and the net force is 0. So for an object in a rotational frame of reference, if the system is at rest, the torques have to cancel because torque is analogous to force. So in this situation, child 1 is applying a force downwards, causing the object to rotate this way. And child 2 is applying a force downwards, causing the system to rotate this way. And in order for this object to be at rest, the torque on the left has to equal the torque on the right. The forces also have to cancel, which means that these two downwards forces here are technically being canceled by the force normal upwards from the fulcrum. Let's work our way slowly into the idea of rotational equilibrium using a concept we're already familiar with. This is Burl the painter, and he is standing on a paint staging. The mass of Burl and the staging itself is 1,200 newtons. In future problems, we'll separate the force of the staging from the force of Burl, but in this problem, we have them combined. So the first question is, which force would each of these spring scales here experience in order to put the situation at equilibrium? And then looking at it, you might already automatically know the answer, that this is 600, 800, and 1,200. And without knowing it, you've already addressed some of the key ideas of rotational equilibrium, that the downwards forces has to equal the upwards forces, for example, or that when Burl is over here closer to the edge, that gives him a smaller radius and therefore a larger force, where here it has a larger radius and a smaller force. On this Burl here on the end, you can see that his radius is 0, essentially, which means that his force is as large as it can possibly be. Let's explore this idea a little further. In this example, you can see that Manuel here has a weight of 1,000 newtons and is standing in the middle of the board with 200 newtons. So you can see in this problem, we are already now separating the weight of Manuel from the weight of the board. And over here in this example, you can see that they are moving farther apart. It says, the ends of the board rest on bathroom scales. Fill in the correct weight reading on each scale. You may already know that if the forces are concentrated here in the center, that the two scales will evenly distribute the weight with each of them reading 600. You may also already instinctively know that if he is standing closer to this edge right here, that this scale will read a higher value and this scale will read a lower value, meaning that the value of this scale over here would be 350 newtons. Once again, you can see that he applies a larger force when he has a smaller radius and a smaller force when he has a larger radius. In this example, a 12-ton truck is a quarter of the way across a bridge with a weight of 20 tons. A 13-ton force is supporting the right side of the bridge. How much support force is on the left side? The downwards force is 32 tons, which means to be at equilibrium, the upwards force also has to be at 32 tons, which leaves this spot right here at 19 tons. In this example, these two objects are applying forces downwards. We have a 4,600 kilogram elephant placed on a massless seesaw with a 0.025 kilogram mouse. The elephant is placed 10 meters from the point of rotation. Where should the mouse sit so that the system is in equilibrium? One of the key parts of this problem is that the seesaw is massless. If the seesaw were not massless, we would have to add an extra force downwards here, which would represent the weight of the seesaw. But since this is a massless seesaw, we don't have to consider that in our problem. For this system to be at rotational equilibrium, that means that the torque produced by the mouse in this direction is going to have to equal the torque produced by the elephant in this direction. So we will set their force times radiuses equal. The force that's supplied by the elephant here is his force of gravity, 4,600 times 9.8, multiplied by a radius of 10. And the sine of the angle that exists between this force and this radius, which is 90 degrees. And we'll set that equal to the mouse. You can see that on both sides of the equation that there are things we can cancel, which gives us a total radius of 1,840,000 meters. I'm located in Detroit, so that's about the distance between Detroit and Roswell, New Mexico. That's a really long seesaw. Let's try another example. It says a wheelbarrow is 1.8 meters long from the handle to the wheel's axle. So here's a wheelbarrow, and here's the distance, 1.8 meters. It says a load of 500 newtons is placed in the wheelbarrow that is a distance of 0.35 meters from the axle. What force is needed to lift the handles? In this problem, the point of rotation is located right here, which means that instead of comparing the torque left to the torque right, we're now comparing the torque up to the torque down. The torque up is the force supplied by the person multiplied by the distance between the person and the point of rotation. We'll set that equal to the force of the wheelbarrow multiplied by the distance between the wheelbarrow and the point of rotation. I calculated that the person has to apply 97.2 newtons of force upwards in order to lift a load of 500 newtons. That is pretty incredible that you can apply only 97 newtons to lift a load of 500, and that's an example of the power of a simple machine. Think of all the work you're saving. In our last example, a wooden plank is balanced on a pivot. Here's our pivot right here. Weights are placed at various places along the plank. We're going to calculate the torque caused by weight A, B, and C. And we're going to assume this is a massless plank. The force that is being applied by object A is due to its force of gravity. So we'll do 2 times 9.8 to get its force of gravity and multiply it by the radius or distance between here and the point of rotation, which is 0.8. That gives us 15.68 Newton meters. Let's try B. 4.41 newtons. That's significantly less. And that happens because it is both a smaller mass and it's significantly closer to the point of rotation. We can now calculate the total torque acting in this direction, which is 20.09 Newton meters. Let's look at C. I got 13.62 Newton meters. When you compare the two sides, 20.09 this way and 13.62 this way, it gives us a net torque of 6.47 Newton meters in this direction, which is positive. That means the plank is not balanced.